Well, I'd like to thank you all for coming here. I was speaking with Drew earlier, just as we began the event. You want me to? I was speaking with Drew earlier, just as we began the event, and he said, if everyone in the world planted a tree, would that help? And how much would that help? And I said, well, certainly would help, but some estimates say that about 60 to 80% of our oxygen, our free oxygen, comes from these little organisms that were mentioned in the ABC video, and that provide our free oxygen, the air that we breathe, the air that everyone breathes. I know when the rainforests were the hot topic of the day, they were called the lungs of the earth, but really the oceans are the lungs of the earth also. They provide us with the bulk of our oxygen. I'm also informed that not everyone here has a huge science background, so we'll just talk a little bit about acidification before we begin. We have a history here of looking at ocean pH and seeing that it does affect the web of life on our planet, not just the little food webs in the ocean, but our whole planet is dependent on it. So if we decrease the pH of the ocean, a lot of students of mine, they get pH mixed up and they think when things become more acidic, the pH rises. But the opposite is true. As things become more acidic, the pH drops. And that H stands for the hydrogen ions, so really we're talking about hydrogen ions in the ocean. But how does carbon dioxide here? Because we have been increasing the carbon dioxide at a steady rate since the turn of the century and before, with the Industrial Revolution, coal fire to begin with, switching to oil, now China chiming in with the coal fire. Again, we're going through a second industrial revolution right now, increasing carbon dioxide exponentially. How does that increase hydrogen? Well, it's carbon dioxide, but what happens is carbon dioxide forms carbonic acid in the atmosphere when it reacts with water, acidifying the rainfall. Also, being the oceans cover 70% of our planet, they absorb a lot of carbon dioxide also. So we're increasing this carbonic acid in the ocean and dropping its pH. If you look at this chart here, you can see this links from glacial time. That was before we became agriculturalists. We were hunter-gatherers at that time, low populations. Pre-industrial, and then the present. We can see the temperature's been rising. You can't get away from climate change here with ocean acidification because we're talking the same elements that cause it, the carbon dioxide. You can see our alkalinity has been changing. The amount of carbonic acid, this is what is causing that pH change, the carbonic acid, has also been rising. There's projections at twice the carbon dioxide from pre-industrial and 3 times, which many projections say that's where we're headed. So you can see that the carbonic acid has been steadily increasing from the carbon dioxide emissions. You can see here's a couple of terms, calcite and aragonite. Important terms. Most non-marine biologists aren't sure, but these shells take the form of calcium carbonate, calcite, aragonite. So that's the key thing here with these little microorganisms, because they're producing these shells. And you can see that with acidification, the free aragonite and calcite is dropping. So this is how we can see how the food chain will be disrupted. You can see that the pH is also dropping. It's slightly basic, so acidification might not be the most accurate term because we're not turning it into an acid, but we're lowering the alkalinity of it. If you would switch. Some possible effects that we can see. We're going to particularly impact those small organisms that use this calcium carbonate to build their skeletons, that form the base of our food chain, that provide us with our oxygen. Just a few examples I'd like to touch on. The Hermatypic corals. There's really two types of corals. Hermatypic corals are the kind that form these beautiful coral reefs that we're so familiar with. They have this little algae that lives in their tissue called it's a type of dinoflagellate called zooxanthellae. And they live in symbiosis and they build these beautiful reefs. Well, these reefs are calcium carbonate based, and we could lose up to 60% of our coral reefs just because of the acidification of the oceans. The Coralline algae is another player in our coral reef communities that uses calcium carbonate, again, to build its cell walls, and it provides a lot of the structure in these systems. It also forms the base of the food chain, that because it is an algae, so it's a producer, it forms the base of these ocean food chains. We also have cold water corals, because not all corals contain the zooxanthellae. They don't all build reefs. We do have cold water corals. They do provide a lot of our economically rich communities. As you can see, a lot of our North Atlantic is cold water coral. And so they're widely distributed, but we could lose up to 70% of these communities also due to the acidification process. When I first started in oceanography, and I saw these words, I had no idea that these existed. And these, the Coccolithophores, Foraminifera, Pteropods, we can add diatoms and all these little critters really form the base of these ocean food webs. Coccoliths are so small that you can really only distinguish them with an electron microscope. Yet, you can see blooms of them from a satellite because they're so plentiful during certain times of the year. It's really amazing. We're talking trillions. And the Foraminifera, another mouthful of a word. If you got that in Scrabble, I tell you, you'd be an instant winner, I'm sure. But these are little animals, and they graze on these algae. They all use calcium carbonate. The pteropods. Pteropods are like little snails. They're mollusks. And they graze on the little algae. So both the primary producers and the primary consumers use calcium carbonate in their bodies. And as we reduce this calcium carbonate saturation, we're removing the first two links of our food chain. So can you imagine what happens to the higher links when you pull the first two links out? Well, let's see. The large marine organisms, the partial pressures will not only affect the physiology of these animals, but it will also disrupt the food chain. So, as you go up through the food chain, everything in our ocean will be affected, and then it will spill over to land-based creatures, also us included. Some of the past events, because we have seen changes in acidity in our ocean's history, they seem to coincide with bad times for life. Okay, so we do have basis for to say, hey, life on Earth really is dependent on our oceans, and alkalinity and acidity do affect life on Earth. In the fossil record, we see several extinction boundaries also have quite acidic oceans. Okay, well, I'd like to thank you guys.